Okay, good afternoon, everyone. My name is Pie Chu Seng Yao. I'm from Industrial Engineering Department. Today, I'm going to present about my final year project poster titled Improving Throughput for an Automated Conveyor Line Subject to Raw Material Availability Constraint. So, for the introduction, conveyor system, let me zoom in a little bit. Okay. Conveyor system allow a good company goods and product to be moved quickly and efficiently, as well as allowing big object like car to be moved down a production line. Many industrial sectors such as manufacturing, automotive, and material handling are increasingly using reconfigurable conveyor system into their process because they provide greater flexibility in responding to newer goods and product line while maximizing space utilization. The maximum sustainable rate of flow is defined as the maximum rate at which thing can be flowed or be transported at a constant rate. The impact of a conveyor system failure on the total throughput and cost is also essential aspect that should be studied. So for the problem statement, the company that I study are a air filter manufacturing company. So the conveyor system study manufacture carbon filter media. The media of the carbon filter are manufactured in a lamination production line. The main problem in this production line is there is a significantly large amount of waste produced on the material during lamination process. This high waste produced in the lamination process result in the throughput of the lamination line to be very low. So the objective of this FIP is to identify the root cause and potential solution of the problem in the automated conveyor line, to develop solution to implement and to improve the throughput of the automated conveyor line, and to test and verify the selected solution. In the literature review part, there is total of 15 papers that are reviewed for some method to improve the throughput of the conveyor system before conducting this case study. So the methods including dynamic analysis, VSM. VSM is the value stream mapping. It used to visualize the flow of material and information. Line balancing, root cause analysis, bottleneck analysis, Kaizen, work standardization, optimization, mathematical modeling of the weight of metal structure, modify design, data mining solution, effectiveness matrix, 5S, Six Sigma, and simulation analysis. So in the chosen method are VSM, root cause analysis, and simulation analysis for this FIP. So let's go to the methodology. So to start, we start by data collection of the conveyor system. The data was collected in this year, January and February 2021 at the company. And after data collection, we verify the data, use the data to build a simulation model of the conveyor system, verify and validate the simulation model, and root cause analysis is done to identify the possible solution. And the possible solution is tested to select the best solution to implement. Okay, so let me go through. Okay, so let's focus on this figure. This figure shows that the process flow of the conveyor line. First, the fiber enter the first machine, the belt opener. Then some water are sprayed on the fiber until the between the cutting and scattering system, the bottom layer of screen is entered. Screen is a finely woven lightweight fabric used as the cover of lamination. It used to cover the fiber and carbon as the outer layer of the lamination. So the first bottom part entered between the cutting and scattering machine. Then the carbon was scattered using the scattering machine. The top part of the screen entered between the heater and laminate heater. Then the product is laminated and cut and wind. Okay, so for the next part, so after collecting the data, the company manager and I discuss and agree we continue this project using simulation analysis. So here show that the simulation using witness simulation software. It includes every machine, labor, and breakdown, and all the input and the conveyor line. So during the root cause analysis, we realized that the large waste is not the only problem. There is also low utilization in worker. So continue to this figure, the VSM is constructed, and these are the VSM. Let me explain more details. So firstly, the VSM is the as I mentioned before, the VSM is the transfer the flow of material and information. So we start from the customer. When the customer order the product, it will be sent to the production control center, and production control center will send information to the supplier to order the material, and at the same time send and work order to the start of the machine, the supplier will send the material into the inventory, and the material inventory and flow into the machine. Every block here are processed in the production line, and the small box below every process are the information of the process, like the speed, the length, the productivity, or cycle time. And the tasks are separate into online tasks and offline tasks. Online task is the task that should be done when the machine is running, and offline is the task that should be done when the machine is not running. And here show that all the value added time and non-value added time of the main process of the conveyor. You can see that there is no non-value added time because it is a fully automated conveyor line. And here the bottom part here show the waste of the whole production line, in term of second so it's the input, the waste rate And then after completing the product in the winding machine, it enter the product inventory and sent to the customer. Okay, so based on the root cause analysis, there is total 4 root cause can be discovered. There is the required output dimension is too small. The input stream size is too big. There is an imbalanced workload distribution of the tree. And so based on the root cause, 4 solution is identified. There is increasing the output width, decreasing the input stream width, and reassigning the work, and reduce the number of labor. So you can see that increasing the output width and increasing the output width and decreasing the input stream width greatly reduce the waste produced by the system. And for the reassigning the task, because the utilization of the worker is very low, so it's logical to suspect there is some imbalanced workload distribution among the worker. Like some worker do more work than others, which result in some worker are busy and at most of the time, and some worker are free. So reassigning the task may help, but in this table show that reassigning the tasks will not increase, but change the utilization by a little bit, like within 1% for the machine utilization and labor utilization, and it change the output quantity also by about 1%. And so low utilization may also imply that all the workers are free all the time. So it may be possible to reduce the number of workers from 4 to 3. But some of the tasks like changing screen require 4 workers. But luckily, during the data collection period, a worker is absent for a few days. So it seems that the task also can be done by 3 workers. So I try to reduce the number of workers to 3, and find that it can increase the labor utilization by about 4%, but it reduced the machine utilization to about also 4%, and reduce the output quantity. So this the reassigning the task and reduce the number of labor is infeasible, and the increased output width and decreased input stream width are feasible. So in conclusion, 10 different future models are constructed based on the comparison of these 10 future models, and the current model, it showed that the increasing the output width and decreasing the input stream width are feasible for this production line, and greatly reduce the material waste, while other methods are not feasible. So for the future research recommendation, we can research about the implementation of the selected solution after a period of time. This study and method can be applied on other product type or other production line in the company. The optimum width of the input script scheme can be studied after a production control unit has been set up after a period of time. Alternative method on performing the online and offline tasks can be studied. So that's all for my presentation. Any question?
Okay, thank you, Pierre. Question from the judges.
Maybe I'll go first. Interesting work, Pierre. My question to you is, when I look at the work, it's interesting. However, my comment is basically, I feel that it's somewhat too case specific and somewhat applied, right? So, can you draw any sort of general conclusions from your study so that it has wider applicability?
Production, is it?
Yeah.
Okay. All right. Thank you.
Okay, thank you. Any other question?
Is there any more question? I ask Simon. Maybe you want to ask any question?
Not for me. I just joined in to listen only.
Okay,
Our chairman is here.
Simon, you ask on my behalf, Simon.
Hi, Arlo. Any question?
Yeah. Simon, can you ask on my behalf?
Okay. On your behalf. So this is from industry. You are talking about manufacturing. Just now I remember we have our one of the judge is it also asking about the downtime.
No, that time.
That time, okay. Yeah, just now, just correct me if I'm wrong. Just now you did present about this manufacturing that is a fully automation, right? But I do have a factory also doing manufacturing. Sometimes there is a lot of unforeseen, is it, on manufacturing. So sometimes in between there might be some fault over there, either human error or by human due to some certain uncertainty that will delay on the process. So is there any study onto for example, like what we do on our scheduling, there is this critical path method for this sort of industry or your VSM design. Do you have any of these criteria to look into that to further improve on our manufacturing process for those unforeseen so-called downtime?
Actually, the first for the critical path one, this one only have one main process is like here, so there is no critical path. And you say for the breakdown part, the breakdown part is actually included in the simulation model. Breakdown part separate into one, like planned breakdown and not planned breakdown. Planned breakdown is something like maintenance, changing the role of the product, like or changing the screen, like changing some input, something like that. And the plan breakdown is something like something stuck inside the machine. They need to stop the whole thing and make one. And the whole breakdown schedule, I took like about 3 to 4 months of breakdown schedule from the company, so I can calculate the mean time to repair and mean time between failure of the every kind of breakdown. So to input into this simulation model. So if you ask me how to implement the thing to how to like any solution to prevent the breakdown from happening, but this one is not my focus on FYP lah.
All right.
That's all.
Maybe on your further when you are in industry engineer, as an industry engineer, and then when you work for a factory, normally factory owner would like to shorten the breakdown time. Is that?
Yep.
So for my here from my future research part here, you can see for the last one, alternative method on performing the online offline tests can be studied. So alternative method like safer method or some method can reduce the breakdown time or mean time to repair. We can be studied for future research.
Yeah, that's good. That's good. At least there is some what you call your future research recommendation.
Yeah.
My last question is just I heard that you took
data for implementation, but since MCO, so the whole back part must change to simulation.
Okay.
They also agree we change to simulation. Then they also want the implementation solution for me.
Okay, all right. Because so in conclusion, your data, I can say is not 100% because the factory is not operating 100%, right?
No, for the all the data from for this VSM is 100% one because I did this in January, February one. But for the simulation part, for the back part simulation in the future model, we are using simulation, but with the same data but different kind of like the specification.
All right. Okay. Thank you.